Okay, so today we have Siyu tell us about the background of geometric Langland conjecture. You may start now.
All right. So, good afternoon to all the lecturers. Today I'm going to talk about the geometric Langlands conjecture. It's a quite new topic. Uh, so yeah. So this is my outline of my presentations. So first of all, I will introduce what is the big picture of geometric Langland conjecture and some of the main ingredients using by the experts in this area, and we'll be looking at some constructions and definition, and also I will talk about some of my future work. So first of all, my objective in this project is to explore the motivation of geometric Langland conjecture and some of the modern approaches to tackle it. So let's look at some of the historical background of GLC. The Langlands conjecture first is formulated by Langlands in the late 1960s. Is an attempt to link number theory with representation theory, and afterwards, actually proved that the Langlands correspondence for GL2 over a function field, and Dreamfield actually used the ideas of algebraic geometry and also some moduli space of curves. And with these ideas, Bellison and also Dreamfield again proposed the GLC. And recently, Gascory and Renskin and many others authors claim that they have proved GLC in a series of 5 papers. And in this talk, I will be only focusing on the first paper, roughly the introduction of the first paper. So what is the differences between the Langlands conjecture and geometric Langlands conjecture? Well, Langlands conjecture mostly deal with number fields, and GLC actually deal with function field. So you can think a quick example of function field as the function field of an elliptic curve, where the elliptic curve is defined by the equation y squared equal to s cubed plus as plus b over a field qa, and the function field is actually the function field is defined is actually the ksy k and add on the variable x and y, and this is the function field for this particular curve. And actually, in Langlands conjecture, they are mostly focusing on automorphic forms, and we will not talk about this. But it's actually analogous to like the modulus stack study by the Dreamfield of G bundles on algebraic curves, and also the Galois representation used in Langlands conjecture are somehow related to the local system which is studied in algebraic geometry, then we will be using in this geometric Langlands conjecture. So the main ingredient is actually about the D modules. Here I will not provide first the definition of D modules is quite technical, and I haven't yet to discover all the related definition to link it all. But I will give like the idea of it. So actually, D modules is something what they are looking at is the category of the derived category of these D modules, and D module is somehow like the shift of differential operators add on the bundle G, which is also the G bundle, and the G is somehow like the reductive algebraic group, which for example, we can take G to be like SGLN or SLN and others. So basically, Bellison and Dreamfield started this study in the context of D modules, and recently Gascory and Reskin so aim to construct the geometry Langlands functor in various settings, and they claim that there are some relationship between these settings. So the two settings provided in the paper are the DRAM setting and also the battery setting. So the first one is the DRAM setting, and the second one is the battery setting. So basically, this is a funder. So they claim because this is funder, so we are looking at the categories. So they claim these two categories are equivalent, and also these two categories are equivalent. And in their paper, they claim there is a biconditional relationship between this setting. So once we can prove this, we can imply this, but also the other way. So now we'll be looking at what is a shift. So because I mentioned before that the D modules is really about something like the shift of differential operators. So I'm being studying about the basic first. So what is a shift? So shift is like was it given a topological space. So the pre-shift is defined as follows, and there is maps inside, and one can look at the simple pre-shift example is the skyscraper pre-shift. And once we have pre-shift, we can get to our main goal, which is the shift by by letting our pre-shift to satisfy more relation as follows, and as our pre-shifts must be separated and has gluing property, and they has to follow the details inside. So once we have this, we notice that in this, what is this LS? Actually, this LS is actually related to the local system. So the rough definition about local system is as follows. First of all, we have this is denoted as a shift. Then if let E be a set, then we say this is constant shift with value E if this shift is the shiftification of the pre-shift U to E. And once it's constant, and it's then for given a neighborhood U contained as such that this is a constant shift, then we say this is a locally constant shift. Meaning when we take a small part from a big space and it's locally is a constant over this small neighborhood, then we say it's a local constant shift. And in other words, they call them this is a local system. So we will be looking at this in this talk. I will be more focusing on the moduli space. So in mathematics, we actually concern about how we can actually classify two or more things into the same class based on their common feature. So modular space is actually invented to tackle such a classification problem. So what is a modular space? So in layman terms, it actually consists of three ingredients. The main things is the objects and how we actually parameterize these objects and how we actually say two objects are equivalent or are the same. And also lastly, the families. So it says how can we modulate these objects over certain parameter. So there are two examples, very famous examples. The first one is the moduli space of lines in the plane, and also the moduli of curves. But in this talk, I will be only focusing on the moduli space of lines in the plane. So a very easy construction is like how we actually describe all the lines that pass through the origin. You might think this as actually is a RP1 real projective space, and how we actually produce a parameter to parameterize such line. Actually, we assign each line a parameter theta that measure the angle between the line L and the x-axis taken in counterclockwise direction. And in this construction, we can check that theta is actually between the ranging from 0 to pi. However, we have not yet considered the case that what if the lines are almost horizontal, meaning our theta is close to pi, or also the lines where the theta close to 0. So to do that, actually we have to identify those points at those points 0 and pi by identify them as the same point. So meaning actually there are 2 points. If we consider the half open interval 0 to pi, and we identify the 2 points, actually it's like when a line become a circle and we tie that out, so it become a line a circle beside this picture. So next, since our GLC is looking at categories, so actually there are the experts like Grothendieck actually introduce topologies on category. So to make our category have a topological like structure, Grothendieck introduced this notion of so-called topos, which in other words we call it Grothendieck topology, and it defines the Grothendieck topology as follows by introduce the ideas like analogous to our usual open sets in topological space, with the idea of covering space by this definition. Basically, it consists of the following data, and this is called the covering set, consisting of covering of S, and is a collection of morphism from the object to another object in this category, satisfying the following properties. And one can easily check that our usual topology defines a Grothendieck topology if S is by given that S is a topological space, and we let the category of open sets in X to be the category, and we can now look at the Grothendieck topology on op X, and by this condition, one can verify that is actually the Grothendieck topology by looking at these 3 properties. Then next, what is my future work? So basically, actually, this GLC is somehow related to various topics. So it's somehow about infinity categories, and also moduli stack, as I mentioned before in here is about the moduli stack of the bundle G. So actually why I introduced this Grothendieck topology is actually that there actually the algebraic geometry experts actually develop in this ascending order. Like first of all we build the Grothendieck topology. Afterward we can build the pre-stack and the stack, and afterward with stack satisfy more properties, then we have our moduli stack. So I have still more definitions to go with, so then I can increase I can update my definitions to the stage of moduli stack. And actually GLC is more care about like not the usual algebraic geometry, but it's about the derived algebraic geometry. And the derived algebraic geometry cares about like the derived sets, rings, categories, and even more. So these are my future work. So that's all for me. Thank you.
Okay, thank you, Sui. Do you have any question from the audience or examiner, Jiajin?
Do you just go to the definition of geometric Langlands? You have 2 settings, right? So what is in the new LSG head?
Oh, this for This you mean these two, right?
Yeah, what is the right hand side of the functor?
I know this is called they call the induced coherent shift, and this new is nilpotent. So, but the detailed definition are yet for me
What
to
is
discover.
LSG hat?
Local system add on this G hat G, and this hat G actually is they call the Langland dual group.
So this is in what kind of setting? The base field is what? Is a function?
Function field.
Function field over. What is the residual field of this function field?
Pardon?
So it's a function field over the. What is the characteristic of the function field?
Oh, zero.
Characteristic 0.
Yeah.
So it's like a function over a complex number or real number. Is it?
I think
are you considering things over real number, or you have to assume it's over complex number?
I think they look at complex number.
Okay, it's a function field for a curve over a complex number.
Yeah.
Okay. Okay, what is Bangji?
Bangji. This Bangji is actually how to say? I think if I'm not mistaken, for me, I think it's like the band is like the bundle add on it's a group action add on the means it's like the usual bundle in differential geometry, and we add on the group. Specifically in this context, they care about the reductive linear algebraic group. So the bundle G on is like the bundle on the linear algebraic group. That's what I know for far. Yeah.
Okay. I never understand Bangji actually. Maybe next time you can
Next time
explain
I will.
this for me.
Yeah, sure.
I have a question actually.
Yes.
For the de Rham setting, is this just the like the Riemann-Hilbert correspondence? Is that just what this is?
Yeah. They do mention because of this Riemann something theorem, and then we can prove
that's the
there
correspondence.
there is a correspondence between the setting. Yeah.
Okay. Just checking.
I don't think it's a Riemann-Hilbert correspondence because G and G hat are different.
I was wondering. So yeah, it looks similar, but I feel like
it's not.
I'm not sure. Okay, so it's not.
It should not be.
It should not be. Okay.
Yeah.
Is it a generalization, or is it just completely unrelated? Because the Riemann-Hilbert also like connects like a modular category with the category of perverse sheaves.
Yes, but the other side is a local system, not perverse sheaf.
Yeah,
I don't know
true.
how to define this Indo sheet category of coherent but still nilpotent. I don't know what it is. Yeah.
Okay, thanks.
Yeah, you should explain. Yeah, just to explain the both sides, it's already like a big things.
Very deep. Many definition to like dig with.
Yeah. Maybe next time the next M maybe is to like spell out the definition. Maybe give an basic example for this equivalence.
Sure.
That could help. Okay.
Any more question?
If no question, maybe we should end here. We should go to the next talk. Okay. Thank you.
Thank you, everyone.